This series explores the foundations of geometry and analysis, questioning the starting definitions that are often accepted in mathematics without a clear, logical demonstration. Advanced systems like set theory are frequently adopted through academic consensus, a process that can obscure the underlying logic for those first learning the subject. Rigorous logic should be transparent from the ground up, remaining accessible and verifiable to anyone willing to follow the steps from the beginning. We are building a framework for mathematics that starts from the first principles, requiring no prior familiarity with complex jargon or axiomatic systems. To reach that level of clarity, we will work under a specific constraint. We must set aside the sophisticated notations and assumptions found in textbooks. Reaching an objective understanding of these concepts requires a willingness to revisit the basics and start the journey from zero. We begin with a starting point that anyone can agree upon, an empty page, nothing. This blank state provides a workspace free of pre-existing mathematical entities, biases, or historical baggage. The first step of mathematical creation is the conscious decision to introduce a single entity into this void. We will not use the Hindu-Arabic numeral system yet. The symbols for 1, 2, and 3 are abstract technologies that we have not yet defined within this new framework. Relying on familiar digits immediately would bypass the foundational logic required to understand what a number represents. By refusing to import outside symbols and building strictly from the empty page, we ensure the foundation remains free of hidden assumptions. We introduce the first mathematical object into our reality, a single discrete stroke. We assign this specific vertical mark the spoken name 1. Now we establish the first operation. We take the entity we have and add another stroke right next to it. Moving from one number to the next is the successor function. The successor of our first entity is a new object, comprised of the original and new stroke. By repeating this successor function, we generate a naturally ordered sequence of these objects. The execution of this successor function generates every natural number in the sequence, providing the first building block for our arithmetic. The shapes we typically use for 3, 4, and 5 are symbols for an underlying reality, strings of strokes. We can now state our formal definition. A natural number is a discrete string of ones. The spoken words 3 or 5 are linguistic names we give to these specific string lengths, rather than independent entities. Standard notation often obscures the physical scale and the direct, tangible relationships between numbers. Treating a symbol like 5 as a starting point, rather than a collection of units, can lead to a less precise understanding of mathematical structure. To maintain rigor, we will view numbers strictly as their constituent physical strings. We can apply this definition to a practical problem, determining the quantitate of a disorganized set of physical objects. The process of counting these shapes is a physical mapping protocol. Following the one-to-one correspondence rule, we generate exactly one stroke on the page for every physical object we identify. When every object is accounted for, the individual strokes are gathered into an ordered sequence. This resulting string is the objective mathematical representation of the physical group. Counting is the creation of a physical record through the application of this struct mapping. Now we must determine the relative size between two distinct numbers without relying on pre-assigned values. Consider these two objects, a top string of ones and a bottom string of ones. We determine their relationship through the physical pairing of their constituent strokes. Equality means every stroke in the first sequence pairs with one in the second, without remainders. To test inequality, we connect the two strings, pairing them one by one. Inequality is proven when pairing ends and one sequence retains unpaired strokes. The presence of these leftovers indicates that the first string comes before the second in the natural sequence. Relations like size and equality are the direct mechanical outcomes of this pairing process. To discuss these mechanics universally, we can use notation that represents any general string of ones. We introduce variables, assigning letters to stand in for these strings. N equals M means the strokes in string N pair perfectly with string M. N is less than M means leftover strokes remain in string M after pairing. These letters are placeholders for the actual strings of strokes. Maintaining this link to a physical operation ensures the logic of our abstraction remains verifiable. Starting from the beginning, we have established a definition of natural numbers and relative size. This framework relies on simple physical logic rather than assumed conventions. This definition of a number as a string of ones serves as the basis for the concepts we will develop next. By starting with these simple steps, we ensure the components of the system fit together without forced rules. Our next step is to apply this framework to the fundamental operations of arithmetic: addition, subtraction, multiplication, and division. Establishing these definitions first creates a foundation for the arithmetic operations we will develop in the next lesson.